Hello, this is Jack Jackson. In our last video, we looked at limits where x was approaching c, but y was approaching infinity or negative infinity, at least from one side. In this video, we're going to look at sort of the opposite thing, where x is going to infinity or minus infinity, but y is going toward a constant. So the other version was when x goes to c and y goes to infinity or minus infinity, that gives you a vertical asymptote. One of the things, not the only thing, but one of the things that could happen here, if x approaches a limit, x approaches infinity or minus infinity, and y approaches a constant, that's one thing that could be a horizontal asymptote. In some way or another, it's approaching a horizontal line. So, like the last couple of applets that we have gone over, this is a GeoGebra applet. This one I wrote. You can find them at geogebra.org. Type in your formula right here. So in our case, I'm using, for the moment, the 3x minus 4 divided by x minus 1, the rational function. Notice that this is undefined when x equals 1, and that's where you have a vertical asymptote. But we also may notice that this levels out to a horizontal line, in this case a horizontal asymptote, actually of y equals 3, as we go out to the far right or far left. When we're evaluating or examining these limits as x goes to minus infinity, far left, or x equals positive infinity, far right, we call that end behavior. It's a little bit of a misnomer because truly this function really doesn't have an end. It goes to the left forever and to the right forever. But we use that meaning anyway. What happens out on the far extremes of this function? So here's the actual definition down here. So given a function f and a real number L, we say that the limit as x goes to infinity of f of x equals L, and it shouldn't have that horizontal line. If and only if for any epsilon greater than 0, there exists a m greater than 0, such that if x is greater than m, then f of x is close to L, well, that is within epsilon of L. That is, L minus epsilon is less than f of x, which is less than L plus epsilon. Similarly, we take the limit as x goes to minus infinity, says that there exists a positive m such that if x is less than the opposite of m, again, L minus epsilon is less than f of x is less than L plus epsilon. So it's very similar to what we did before. We have our epsilon limits here. So we have our limit, which we think is 3 here. So that graphs the horizontal line right there, y equals 3, which I can change by typing in that box. I'll have to change it for different functions if I change the formula for my function. And I choose a value of epsilon, say I pick epsilon as 1, and that defines a horizontal line here at y equals L plus epsilon. 3 plus 1 is 4, so that's y equals 4. And then L minus epsilon, y equals that, so that's y equals 3 minus 1, that's y equals 2. So we have y equals 2, y equals 4. That defines the top and bottom strips here. If we're looking out to the right of m, here's m. I can actually adjust it with this here by just kind of sliding this point here. Or I can, yeah, actually that's how we do this one, is by that, is by moving this point. And so by moving this point here, it determines the value of m. And so we're, if we want to do the right end behavior, then we're talking about the limit as x goes to infinity. We're looking at the little blue box over here on the right. But at the same time, this same picture examines what happens on the left end behavior, that is the limit as x goes to minus infinity. In this case, the answer is that they both have the same limit, or the function has the same limit on both sides. It is that it's approaching 3. So how close to 3 do you need to be? Well, you need to be within that that part of the graph. Now, if you look right now, that's not a good choice for m because there are parts of things to the right of m which have y values on the graph that are outside of this strip. In other words, the graph is sticking out of this horizontal strip. But if I go enough, like right there wherever that crosses, that might be right at 2, it's okay if it goes to a corner. Now anything to the right of that is going to be in the box. Of course, anytime I find something that works, anything further out will work because now those are certainly within the same box. Now the point is if I make epsilon smaller, say maybe I go to a half, then this same thing that worked for epsilon equals 1 may no longer work now when epsilon is smaller. See, now it's sticking out, so I need to make what I do. No problem, I just make a bigger m. Say I could go to there or anything to the right of that. And now the graph is staying inside that little strip. Okay, and the point is no matter how small I make epsilon, there's somewhere I can go to make m large enough so that the graph always stays within. In a similar manner, the limit to the left is also 3 because no matter how big I make m, which makes the minus m, I can make it minus m go farther enough to the left, i.e. make m bigger, so that I stay within the bounds of this here. And in this case, the m could have been quite a bit smaller. Yeah, even back here is going to stay within on the left side. Maybe not on the right side, but on the left it is. So if we go further out, definitely we're staying within there. Okay, make a smaller epsilon. Well, I might need to go further out, possibly. The smallest value of m that would work would be where that crosses right there. So you can get an idea of how what it means to have a horizontal, well, have a limit as x approaches infinity or minus infinity. Now, there's actually several ways this could happen. This could actually be a horizontal line from some point on out. That would be okay. Another thing is what we have here, which is an asymptote. So from some point on, this graph does not touch the asymptote, but gets closer and closer and closer to it. That's asymptotic behavior. Now, it might touch the graph, might touch that horizontal asymptote somewhere else. This one doesn't, but some could in the middle part here. But from some point out, it doesn't touch that horizontal line, but it gets closer and closer to it as we go out. That's a horizontal asymptote. There are other types of ways you could still have the same limit. You could approach this line by maybe something called damped oscillation, where it's going up and down, above and below the line, but less and less and less each time. So there are a number of different ways that you could have the graph approach a horizontal line, in which case the limit would actually exist as x approaches infinity or minus infinity. Hope you will find this little app useful for you.